Bungee. It's a bit of a classic, this one, and I've seen this in exam papers before. There's several calculations that we can do. The first one is the speed when the rope becomes stretched. So all we're doing here is, you could use a suvat, but I'm just going to make the shortcut root 2gh for the velocity of an object that's fallen from a height h. That's going to be the square root of 2 times 9.81 times 30. So we get 24.26 for that bit. Now, the distance x. So this is the unstretched length here, and this is equilibrium. And at equilibrium, that's where the bungee jumper will eventually stop. So it's when the force is going to be 0, and therefore the weight must balance the tension in the bungee rope. And the extension that I'm using here is the same x because of the definition of L that's given. So that allows me to work out the extension. Divide that by the spring constant. So I'm just going to work that out. 57 times 9.81 divided by 68. 8.22 meters. 8.22 meters. Let's make a bit of space here. And look at the next one. It says now the jumper moves with simple harmonic motion. Big hint, we've got to use one of those equations, and they're looking for the time taken, which it could be something to do with the period of SHM. Now, thinking about what's happening from equilibrium, bungee jumper moves down, and then they're about to go back up, and one full period would be what I've drawn here. But we don't want the full period, we just want to the lowest point, which is here, and that is just 1/4 of the period. And we can therefore work out 1/4 of the period, which is going to be 1/4 of 2 pi times the square root of the mass divided by the spring constant. We know all of those things, so just going to plug those in. 2 times pi divided by 4, mass 57, spring constant 68. That gives me 1.44 seconds, which seems quite sensible. Then it says, using your first, second, and third answers, calculate A, the amplitude of the oscillation. Now, I've written the equation that you need for this one up here. That is one way of doing it. The other way is to conserve energy. So one way to do this, it's the first time I've done it, but I'm going to try it here. We know the velocity here, which is also linked to the kinetic energy. And we know the extension at that point in the form of the potential energy. By the time the bungee jumper gets down to the bottom there will be no kinetic energy, and therefore only potential energy, and by definition the extension at that point is also equal to the amplitude as is labelled. Either equation will get you there. I'm just going to carry on with what I've done here, so I'm going to get rid of the half. And I'm looking for A, the amplitude, so I'm going to divide by K. And then I'm going to take the square root of that thing. So plugging it all in, mv squared over k, 57, times 24.26 squared divided by k, 68, plus 8.22 squared. Then take the square root of that thing, and that gives us the amplitude, which is 23.68 meters. And the equation there at the top, that should also work. You've got to get omega as well.